Hello everybody. This is a video about two very beautiful and interesting irrationality proofs at a glance. First of all, what is an irrational number really? To answer this question, one has to first understand about rational numbers, or what a rational number really is. A rational number can be written as a ratio of two integers, and is characterized by the fact that it either terminates or it recurs, or just recurs as you wish, in any base 2, base 3, base 10 decimal, or hexadecimal even, or in any base really. We'll for now only consider decimal. If an integer, b, for example, for the sake of it, divides another integer, a, for example, one has b possible choices for the remaining portion left after the division. Well, this we call remainder. So if b is, for example, 13, then there are 13 possible choices for a remainder, 0, 1, 2, 3, and so on, up to 12. Rational numbers again. So let's consider some examples to understand the concept of rational and irrational numbers. Well, you all know this, but let's just recap again. 1 over 4, for example, in decimal is 0.25000, because 4 fits into 1 0 times in the 10th position, so 1 after the decimal place twice, then 5 times, and then 0 times, so it fits in perfectly and leaves no remainder. 5 over 5 likewise is 1.000, that's the same number. 13 over 7 is slightly more complicated, but we can still understand it. It's a recurring number, so it can be written as 1 plus 6 over 7. Now 7 is larger than 6, so we can write this as 1 over 10 times 10 plus 60 over 7. So we can now divide 60 by 7 again and see that it fits in 8 times with remainder 4. And then we can keep continuing this process to understand that 13 over 7 is in fact 1.857142, 857,142, and so on. So it recurs and has this recurring number 857,142. Okay, so now let's try to understand what an irrational number is. An irrational number, like the name suggests, is not rational. It's not a ratio of integers, and does therefore not terminate or recur. Some famous examples are, for example, root 2 or root 3, e, the number pi, or even log base 3 of 10. Those are all irrational numbers. Okay, let's now consider the first proof. This is truly marvelous, and it really illustrates a really basic concept of irrationality, and it's really simple to portray. What does this first summation sign mean? Well, this means you sum, that's important, sigma for summing, it's Greek letter sigma, from n equals 1 to infinity, so you plug in all square numbers. This is base 10, so it could be binary, that would be 2, but this is now 10 for base 10 decimal, and you're feeding in 1, so 1 squared, then 2, 2 squared, 3, 3 squared, and so on, 1, 4, 9, 16, and so on. And then you add them, so you add 1 over 10, plus 1 over 10,000, plus 1 over 10 to the 9, and so on, and you can keep continuing this to infinity. This resulting number, is then 0.100100001, and so on, so it has a 1 at position 1, 4, 9, 16, and so on. Does this number terminate? No, because there's always another square number. Does this number recur? No, because the gaps between the square numbers increase. They increase in terms of the odd numbers. The first odd number is 1, then you add 3 to get 4, you add 5 to get 9, you add 7 to get 16, you add 9 to get 25, and so on. So they always increase the gaps, but then this number can't recur, because a recurring number is defined as a portion continues forever, but then the gaps between these ones always increases, so there can't be a portion that of numbers that always continues forever. Hence this number does not recur. But if it doesn't recur or terminate, then it is rational. It is not rational, it's irrational, and that's the proof. The second proof is really marvelous, and it takes one of my favourite concepts about number theory, which is prime numbers. Prime numbers, as you all know probably, are numbers that are only divisible by themselves and 1. And you can construct a very similar number, but very different in nature as well, but it's also irrational, and we can prove this. We again sum from n equals 1 to infinity of 1 over 10 to the prime n. So if you have the n equals 1, that would be 2, n equals 2, that would be 3, n equals 3, that would be 5, 2, 3, 5, 7, 11. You all know these numbers, those are the prime numbers. So you get a decimal number which is 0.01101010001 and so on. So you have a 1 at every prime number and a 0 at every composite number. Can this number terminate? Well, no, because of Euclid. Euclid showed that there are infinitely many prime numbers. There's always another 1 in this sequence. Hence, it can't go 0, 0, 0 forever after some point, because there's always another 1. Hence, this number does not terminate. That's the first step in our proof. The second argument we must make is that this number that I'm going to write down again can't recur either. Why? Because if it could recur, there would be a prime, p, a large prime say, after which a sequence of prime gaps always recurs. What do I mean by that? Well, say a really large prime in the millions or trillions or whatever, that prime, after that, another prime, say a twin prime, after that another prime comes after a sequence of 2. So a really large number, and then 2 afterwards a prime comes. Then 18 afterwards a prime comes. Then 420 afterwards, so a large prime comes. Okay, and then that sequence recurs 2, 18, 420, 2, 18. That's what I'm saying. Because the gaps between the primes here are the prime gaps because of 10 to the prime n. Hence, that's why we're saying that the prime gaps would have to recur, not the primes itself, but the prime gaps would have to recur. Let's say 2 plus 18 plus 420, that would be 440. Say this sequence, that's the sequence of all prime numbers, and all these numbers in that list are prime by definition because they're on this list. That sequence, say now it has got length 440, but say this sequence has length n, p plus np must be prime. Why? So in this case, that large prime, p plus 440 times that prime would be prime because this large prime p plus 2, then another 4 on, and then another 18 on, and then another 420 on, those numbers would always be prime. Hence, p plus np would also be prime. But that can be factored, that number. It's composite. That's a contradiction. Well, that must mean if it can't terminate or recur, because we just came to a contradiction, it's not rational again, so it must be irrational. And that leads us to our conclusion that this number is irrational. A gorgeous proof. Hope you enjoyed it as much as I did. Thank you for watching.